transformations of functions and graphing. And I asked you guys to work on the worksheet 1 there for homework. How did that go?
That was actually pretty swell.
Yeah,
It was okay?
yeah.
Wasn't anything.
Yeah, it shouldn't have been. Should have been relatively doable. Okay. Well, today then, we're going to be kind of continuing with that same idea, but this time in regard to let's do that, to sine and cosine functions. So last time we talked about how for a parent function y equals f of x, we can take some resultant function and think about it as a transformation of that parent function, right? So in this section 3.1, our f of x is going to be either the function sine x or cosine x. So our first order of business is going to be to, well, like, what does the graph of sine or the graph of cosine really look like, right? We need to have some intuition about what those things look like. So if we're going to transform them, like, what is it going to look like if I reflect it, or I shift it, or I stretch it, or I shrink it, or, you know, do one of these transformations to it? But is okay with that idea? Okay. So to do that, what we're going to do is we're going to be using the unit circle. So I'm going to go ahead and do that. And I'm going to use the unit circle to plot some points. So this piece of software I'm using right now is just like a way to graph functions or whatever. I'm just going to use it because it's convenient for me to type the points in and have it plot the points, and then I can graph something on top. It's just a convenient tool for what we're about to do. The process we're about to do is not something I'd ask you to repeat, but I want you to understand kind of how we go about constructing a graph for sine or cosine naively, right, without the shortcuts that we're going to show you. Everybody's okay with that? Okay. So when I think about the function, like f of x equals sine x, what is the x here that we're going to be plugging in? Right? What kind of thing do we plug into sine? It's an angle measure, right? That's good. And we have two types of angle measures, right? We've talked about degrees and radians. Which one do you suppose we use when we're graphing? We use radians when we're graphing. The reason being, to graph like the full unit circle, how many degrees am I going to need? 360. So that's like 360 tick marks on my x-axis. How many radians do I need to graph one full unit circle? 2 pi? And how much is 2 pi?
180.
Just a little bit more than 6, right? The number 2 pi, 2 times 3.14 is just a little bit more than 6. So like, would you rather make like a little bit more than 6 tick marks or 360 tick marks? A little bit more than 6. So that's why we use radians when we're graphing, is it's just a little bit more convenient to draw out that x-axis rather than having, have to worry about 360 tick marks. Everybody's cool? Okay. So if I am going to graph my sine function, then what I'm going to do is I'm going to start by plugging in 0 radians, and I know the value for sine of 0 is going to come from the y coordinate, so that would be 0. So the first point that I'm going to plot would be 0, 0. And then the next point I'll plot will be pi over 6, 1/2, because sine of pi over 6 is equal to 1/2, right? This is just how we use the unit circle. Okay. And then we'll do pi over 4 and square root 2 over 2. I'm just going to write that as a decimal when I'm typing this in. So square root 2 over 2 is about 0.707. It's just easier than trying to type the square root in.
You just know that off the top of your head.
Yeah. Again, look, remember, how many years have I been doing this? Like 15 years I've been doing this. Imagine doing the same class 15 years in a row. And you have to know it so well those 15 years in a row that you can teach it to other people. So you have to be able to like answer all of their questions. That's why I know stuff like this. It's not because like, oh, I'm good at math. I do know everything. But that's, again, like, been doing this for a long, long time. And no, I haven't taught trigonometry every one of those 15 years, but you can be impressed, but I'm letting you know that like, this is not like, I don't do this casually. This is not an accident that I know these things. It's because I've been doing this for a long time and I've tried very hard to be good at it, Kate.
What's your favorite one to teach?
Well, I don't know. I think that all the classes have like interesting or cool pieces to them. It more has to do with like how interested the students are on like being interested in what we're doing. You know what I mean? Like that really makes or breaks what ends up being a fun year or not. To be honest with you, at this level anyways, like all of this stuff I'm doing, even like the AP calculus stuff that we're doing, is not difficult. Like for me, it's not like super, super interesting. Content-wise, like some of it's kind of neat, but like the stuff that's neat is, like is only fun if the students are interested in what we're doing also. You know what I mean? So I'm just going to kind of continue going through and doing this. So each place on the unit circle is generating a point for me. And at this point, I'm going to stop highlighting things on the unit circle. I'm just going to type. Is that cool with you guys?
Yeah.
Okay. So what I want you to do while I'm typing this is take a close look at what it is that, or the picture that we're getting out of this. What does it appear that's happening? So that's one full trip around the unit circle, just plotting the points for sine. And if I were to continue going, I would just continue going around the unit circle again. So I'd get another repeat of what we just graphed, right? So
Yeah.
correct. This is just the graph for sine. Yep. We'll do cosine here in a minute. So if I graph sine, this is what it looks like. You notice it's passing exactly through the points that we just graphed. And it's just going to repeat that pattern over and over again because every trip around the unit circle gives me another one of these up and down waves, right? Is this so far okay, Olivia? Okay. I know I kind of cut you off there. I didn't know if you're in the middle of something. Sometimes I just get excited. I mean, we're doing math here, guys. All right. So let's drop that image that we just created in here. Oh boy, that's not where I wanted that to go. Everybody okay with that? What we just created? Let's do the same thing now for cosine. Right? Because that's the obvious next question. Like, okay, Mr. Quillett, great. That's fine for sine. But what about cosine? So cosine, what we're going to do is the x value is still the input for the angle. But the value for cosine of x is going to be the x coordinate from our unit circle. Everybody's okay with that? So all I'm going to do, notice the points that we're plotting, the x coordinate stays the same each time. The y coordinate is all that's changing. So I'm just going to go and update these y coordinates. The x coordinate from the unit circle, because those are the values for cosine, right? So we're graphing cosine right now.
So even though it's the x value on the unit circle, you plug it in as the y value?
Right, because what we're graphing is f of x equals cosine x. So the y coordinate is the value of cosine x, which is the x coordinate from the unit circle, right? And then where were we? So we're okay. So this is what we get for cosine. And if we kept going, we would have the same thing over and over again, right? Because we're just making trips around the unit circle. So if I graph cosine, that passes to exactly through the points that we just plotted. Is that okay with everybody? What is going on here? That's weird. Why did it make it so small? I don't even really know. So take a moment and look at the two graphs here for sine and cosine. Think about the vocabulary we have for transformations. What do you notice here? They look the same, except they are shifted left or right by some amount, correct? Like I could turn the graph of sine into cosine by like sliding it to the left a little bit or sliding it to the right a little bit more. Everybody agree with that?
Yeah.
Or I could do the same thing with cosine and make it look exactly like sine by sliding it to the right a little bit or sliding it to the left a little bit. Everybody agree with that?
Yeah.
But essentially they're the same picture. They're just a transformation of one another. Is that okay? That'll be an important observation here for next time. But right now, I'm just going to point that out, that they're really the same shape, that I can turn any graph of a sine function into a cosine function just by translating it to the right or left a little bit, and vice versa. Okay. So we have a little bit of vocab here to talk about now. Actually, let's do it over here underneath one of these pictures because I'll refer to one of these pictures while I do this. So when we talk about a graph of a sine or cosine function, just FYI that these guys, this type of graph that looks like a wave like that is called a sinusoid. So that's the word we use to describe this wave shape. So we'd say that these are graphs of sinusoids. Okay. And notice how these waves repeat. This is what we'd call these examples of periodic functions. So that means that they're repeating over and over. So if you have a function that repeats the same pattern over and over like this, call that a periodic function. This is a periodic sinusoid function. So it tells you that it's repeating over and over, and its shape is like a wave. What do you guys think? Is that okay, vocab-wise? All right. Now, when we talk about one of these sinusoids, there's a few like descriptors that can describe what the sinusoid looks like that are going to be important for us. So the first thing we want to talk about is the midline. So the midline is a horizontal line that divides the graph in half. So for the graph of sine, that would be our midline. And for the graph of cosine, that's still going to be our midline. Notice that there's an equal amount of the graph above the midline as there is below the midline. So they're both located in the same place. I'm going to color code these attributes so that I can get away without having to label the graphs and get everything like too crazy. The next attribute I want to talk about is the amplitude. So the amplitude is the distance from an extrema to the midline. What is it? What do I mean when I say an extrema? A minimum or maximum. So for example, here, that distance could be an amplitude. What does that distance appear to be? 1, right? You can tell kind of right here is, looks like 1. Everybody's okay? And doesn't matter where you measured from, right? Whether it's a max or a min, that amplitude is the same, and it's the same whether you're looking at a sine graph or a cosine graph. Well, the amplitude's a measure of distance, so distance is always positive, right? So it's the distance from the midline to an extrema, always positive. Excellent observation. Everybody okay with what an amplitude is? Okay. The next thing we'll talk about is the period. Oops, I didn't write down what that was. Okay. So the period is the length of the longest non-repeating segment of the graph So what I like to think about a period as is like an up piece and then a down piece, or you could think about it from like up to up. Anything like that is fine. So if I look at my graph of sine here, that's going to be one period. Everybody feel okay with that? So when we talk about a period, we're talking about the horizontal distance. So we started at 0, 0, and we ended at 2 pi comma 0. So how far horizontally did that travel? 2 pi. Everybody agree with that? Okay. If I look at the cosine graph, maybe this time we'll go from maximum to maximum. That's also one period. Also has the length of 2 pi. Is everybody okay with that? Okay. And then there's one more attribute that we want to talk about, and that is the frequency. Now, the definition for the frequency is the number of wave cycles completed in 1 unit. So if I think about that, hi, come on in. There's chairs if you want to sit, or standing is fine. You're welcome. So if we think about that definition, the frequency is 1 unit per period. Ugh, spelling. So in the case of our sine and cosine graphs, just going to be 1 over 2 pi. Okay, so just the rate. So it's saying in 1 unit, we do 1 2/5 of our period. Right? So like going from 0 to 1, ugh, don't do that. You know, like maybe here, How much did we cover? Like basically 1/6-ish of a period, which is kind of what it looks like, right? If you lined up 6 of those, it'd be cover about the entire length of our period. That's all we're saying with the frequency. It's just another way of describing like how wavy our graph is. Okay with that idea? Okay. All right. So that's our 4 key descriptors that we have for our sine and cosine graphs. We describe them by talking about their amplitude and their period and their frequency and their midline. Let's now take these ideas and relate them all back to this transformation of functions thing. Okay with that? So if I take our parent function f of x and our resultant function g of x equals, no problem, a times g of 1 over c x minus h plus k, no problem. But this time we want to talk about, say, sine x as our parent function. So if I do that, our resultant function just becomes a times sine of 1 over c times x minus h plus k. Or if we took cosine as our parent function, the resultant function would be a times cosine of 1 over c times x minus h plus k. And remember what we talked about last time with these resultant functions. We talked about how to use them, or how to use them to identify the values for AC, H, and K. We could use the values for AC, H, and K to verbally describe the type of transformation occurring. And by using some points from the parent function, we could use that to the AC, H, and K to transform those parent function points into points in the resultant function to create a graph. We're going to do all those same things now, but instead of using, like I think yesterday, the parent function we used in all of our examples was x squared, we're just going to be using sine and cosine. Okay. Well, let's do a couple of examples, since it's really the same techniques as yesterday. So let's say we have the parent function is y equals sine x. Let's say we have this transformation. So just like yesterday, my first order of business is to rewrite this in that general transformation form so I can pull the values for A, C, H, and K. So that was our general form. So if I start rewriting now, -2 sine of, and now I have to rewrite 2x as 1 over c times x minus h, right? Olivia, can you sit down? Thank you. I want to take 2x and write that as 1 over c times x minus h. Everybody's okay with that? So first things first, down here I notice the coefficient on my x needs to be 1. Up here that coefficient is 2. So I'm going to write it as like 2 times x. Notice there's nothing that's being added or subtracted inside of that or next to that 2x. So that tells me the h has to be 0, right? Because if we're not doing anything, that meant we would be adding or subtracting 0. And then we have the -1 at the end. But we still have to kind of worry about this 2 out front, because that's not quite written as 1 over c. Right? How do I write 2 as a unit fraction? I write as 1 over a half, right? That's basically like taking the reciprocal of 2 twice. If I take 2 and I flip it once, I get a half. If I flip it again, I get 2 back, right? We're just flipping twice. But the point of this, what this gives me, is it makes it really easy to identify the values for A, C, H, and K. And just like yesterday, or I'm sorry, last time, not yesterday, we can use our criteria for the transformation to describe what's going on. So let's grab that criteria from last time so that we can, because it's been a minute. We'll drop that back in here. Boop. All right. So if we look at our C's, our C is positive. So we have, according to our criteria, no reflection across the y-axis. Bye. No problem. Have a great day. And because our C is between, or is less, our absolute value C is less than 1, it tells me we have a horizontal shrink by a factor of 1/2. Since our A value is negative, it tells us we have a reflection across the x-axis. Since the magnitude of our A is bigger than 1, we have a vertical stretch by a factor of 2. Since our H is 0, we have no horizontal shift. And because our K is negative, we know we're going down and then 1 unit. So far, is this any different than what we did last time? It's identical, right? The only thing that's different is the function we're talking about is sine instead of x squared, but like, it really doesn't make any difference, right? The process of pulling the values for A, C, H, and K and then interpreting them as transformations remains identical. Boyd. Of course. Okay. What was the other thing that we did last time? We graphed them, right? So let's do that with this same trig function here. So to graph this, we needed points from the parent function to transform. So if we look at our sheet here, so I've put this sheet into the OneNote. This is the reference points for the trig functions. Since we're using sine, these are the reference points we'll use every time. When we do our cosine example, those will be the reference points we'll use for cosine every time. Where did these points come from? These are some of the points we just plotted at the start, right? These are just values from the unit circle. Notice they're not all the values from the unit circle. If we go back and we look at our graph of sine here that we graphed at the beginning, oops. We are just using those 5. The extrema and the midline points. That's all we're using. We don't need to use all the points on the unit circle. We just need those 5. That'll be enough to get us a good picture. Okay? So let's go back to that example we were working on. All right. So last time, we talked about how we can take our points from the parent function and transform them into a resultant function by using this map c times x plus h, comma ay plus k. So if we plug in our values from this example, our c was 1/2, our h was 0, our a was -2, and our k was -1. And we're going to use those reference points that we were just looking at a moment ago. Those would be things that I would provide for you in a test setting. You would not need to memorize the reference points. So that's not shouldn't be a concern for us. So all we're doing now is we're just going to plug in the x and y from the parent function into the x and y in our map and simplify. So when I plug in 0, 1/2 times 0 is 0, plus 0 is 0, -2 times 0 is 0, -1 is -1. Plug in pi over 4, or pi over 2. 1/2 times pi over 2 is pi over 4. And then -2 times 1 is -1, -1 is -3. I plug in pi. 1/2 times pi is pi over 2. -2 times 0 minus 1 is -1. Plug in 3 over 2, so 1/2 times 3 over 2 pi is 3 over 4 pi. -2 times -1 is 2, minus 1 is 1. And then the last one, plugging in 2 pi, 1/2 times 2 pi is pi. -2 times 0 minus 1 is -1. So this is what we're going to be plotting, right? So let's just grab some graph paper. Okay. So here's my graph paper. So notice the tick marks here are 0 and pi. So halfway in between must be 1/2 a pi and 3 over 2 pi. Everybody's okay with that? So 1/4 pi must be in between the 1/2 and 0. And 3/4 pi must be in between the 1/2 and 1 pi. So that's everything I need. So 0, -1. Let's use a different color. Pi over 4, -3. Pi over 2, -1. 3 pi over 4, +1. And then pi, -1. So if I connect everything, that's what I'd get. Sophia? Sure. Is everybody okay with how I plotted those points? Okay, but I'd say we're not done here. Mr. Kulik's expectation is going to be that you fill the space provided. So I'm not going to generate any more points. I'm just going to use the pattern that we've established to fill in the rest of the space. So I'm going to have, after a midline, I go to the minimum, and then I go back to the midline, and then up to a maximum, back to the midline, down to a minimum, back to the midline. So I'm just going to, well, they're notes, so I'm going to show you that if you go back and look at this, you can see the part that I plotted from the points and the rest of it that I'm just kind of generating. It's probably the way that you'd want to do that. Okay, so doing the same thing here. So we're going to be at the maximum, back to the midline, down to the minimum, back to the midline, maximum, midline, minimum, midline, maximum, midline. And then we'll just kind of fill it in. Everybody okay with that? So again, I didn't generate new points by like continuing to go around my unit circle or whatever. I just kind of followed the pattern and used my eyes to extend the graph in both directions. What do you guys think? Does this feel pretty good so far? Okay. Let's do a cosine example, and I just want to check something real quick. Okay. Okay. Good. Cosine example. So do the same thing here, except here our parent function is going to be cosine. Sure. Oh, how do I want to do this? Yeah, guess that'll be fine. All right. So here's our next example, negative cosine of negative x over 2 plus 3 pi over 4 plus 1. So just like before, I need to start by writing this in that general form for our transformation, just like we did last time. So to do that, what am I going to write? What is the a value here? -1. And then here's the tricky part. I have to take this piece and write it like 1 over c minus h. So what do I have to do any factoring here? What's the coefficient on my x currently? -0.5, right? So I have to factor that off. When I take negative x over 2 and I divide by -0.5, that just becomes positive x. And then when I take positive 3 pi over 4 and I divide by -0.5, well, positive divided by negative is negative. And then what is 3 pi over 4 divided by a half? Who remembers how to divide fractions from elementary school? Yeah, you make a reciprocal and turn it into a multiplication problem. Oops. So I get 3 pi over 2. Is everybody okay with that piece? There, off to the side. Is that okay? You guys remember doing that? I think we had an example where I had to do that last time. Okay. So my value for A is -1. My value for C is -2. Remember, the C is just the denominator of that unit fraction. The value for H is 3 pi over 2. Yep. And the value for K is 1. Now, the number one place where students make a mistake here is they take that negative sign with them on the H. Notice the formula has minus H in it. So the value of H is always the opposite, it appears. Be careful on that. That's an easy place to make a mistake. All right, describing the transformation. C is negative. What does that mean? Means we reflect across the y-axis. Our magnitude of C is greater than 1. What does that mean? Means we have a horizontal stretch and by a factor of 2. Our A is negative. That means we also get a reflection, but this time across the x-axis. And since the magnitude of A is 1, we have no vertical dilation. Since our H is positive, we're going to be shifting right, and then 3 pi over 2 units. And since our K is positive, we're going to be shifting up, and then in this case, just 1 unit. So far, so good. So there's our description. Okay. So just like before, to graph this, we're going to use this same transformation map that we did last time. So again, this is going to take me from a point on the parent function to a point on the transformed function. So I plug in my values for C, H, A, and K into that formula. And now I just need to get the parent or the points from that parent function. Which kind of graph are we doing right now? Cosine. So if I go to the reference point sheet, I'm going to be pulling the points for cosine, the ones that I've circled there in green. So we'll just copy those in. And then once you're a math teacher and have been doing this for half your life or whatever, you can have those points all memorized because you'll have done it so many times, but you don't actually need to memorize them. Although if you're planning on being a math teacher, get a jump on it. It impresses students, like you're all impressed whenever I remember like the decimal approximation for something. Okay, and just like we did before, we're just going to plug the values for x into the x spot and the y's into the y spot and just simplify things down. Negative 2 times 0 plus 3 over 2 is just 3 over 2. Negative 1 plus 1 is 0. Negative 2 times pi over 2 is negative pi, plus 3 pi over 2 is pi over 2. And then negative 0 plus 1 is 1. And then negative 2 times pi plus 3 pi over 2 is negative pi over 2. And negative of negative 1 plus 1 is 2. And then negative 2 times 3 pi over 2 is negative 3 pi plus 3 over 2 pi is negative 3 over 2 pi. And then negative 0 plus 1 is 1. And the last one, negative 2 times 2 pi is negative 4 pi, plus 3 pi over 2 is negative 5 pi over 2. And then negative 1 plus 1 is 0. Take a look at the x-coordinates. Notice that in each case, the pattern remained the same, that we've subtracted pi, 1 pi each time. That's a good self-check to make sure that the pattern on the x-coordinates stays the same, that it's increasing or decreasing by the same amount. That should always happen. If not, you've probably made an arithmetic error. Okay. Let's go ahead and drop in a set of axes and we can plot this out. Okay. So let's see, we have 3 over 2 pi is our first spot. So like that's a half pi, that's 1 pi. So that's like 3.5 pi. Or I'm sorry, 3 over 2 pi. Choose 3 halves pi, not 3.5. Then we have pi over 2, 1. So that would be like there. Now we have to do negative pi over 2. Well, if that's negative pi, that's got to be negative pi over 2. And then negative 3 pi over 2. Well, that's halfway between negative pi and negative 2 pi. So negative 3 pi over 2 and 1. And then negative 5 pi over 2 would be halfway in between negative 2 pi and negative 3 pi, which is probably like right about there if I'm eyeballing it, and that's at 0. So if I graph this then, it's going to look like that. And we're not done though. What do we want to do? Yeah, we just want to extend this to fill the space. There's not much space left. The next space would be like here, and it would be up at 1, be a midline point. So I can just kind of do that to finish off extending, of course. And that's the gist of it. I think that's probably enough for today. So there's a couple of things I want you to work on for your assignment. One of them is this worksheet 2. So worksheet 2, the first page, very similar to worksheet 1. Second page, very similar to worksheet 1. Wait a minute. Is this what I wanted? What do I want? Oh, I want. Okay. All right. That's not what I meant. What I thought I was going to be giving. Hold on one second, guys. We don't need to do this again. This is all the same as worksheet 1. All right, well, let's start here. This I'm ready to do. I want you to do 1 through 4 and 9 through 12. So on 9 through 12, they're asking you to do some graphing. And they're asking you to graph it over either negative 4 pi to 4 pi or negative 2 pi to 2 pi. Let me help you out here and get you an appropriate graph paper. I'm just going to drop that into the homework set here. So there's a set of graph paper that you can graph things between negative 2 pi and positive 2 pi. And then let's get you another one that we can use for negative 4 pi to positive 4 pi, because that was the other set. Maybe we'll do 4.5 pi. That's better. Okay. So if you are doing your stuff in OneNote, those are some graph papers that you can steal to drop into your OneNote. If you click on them, you can resize them so that they're not massive if it's like way too big for what you're doing. So let's do those. And then on worksheet 3, I want you guys to work on 7 through 12. We're not going to worry about the first part of that worksheet 3 yet, though. I haven't done that yet. 7 through 12. Let me double check that one more time. Skulik's already slipped out of his mind. Okay, good. Okay. And this will all be part of the problem set that's due on, what is Sunday, the 9th?
Yeah.
Yeah. So that'll all be part of Sunday's homework set. When we meet again on Thursday, we'll talk about how these transformations are going to affect the midline, the amplitude, the period, the frequency, and then talk about how to go backwards from a picture of the graph to an equation. So that'll be the plan for next time. We'll do those 2 ideas. And then the time after that, we'll talk about, instead of getting the whole graph and going to the equation, what if we just give you some information about the graph and go back to the equation? So that'll be what we'll talk about here the next 2 lessons. Questions about anything so far?
Is it fine if we just like do problems on like a paper in our notebook and upload a photo of that?
Yeah, of course. Yeah, I some people do it in their OneNote, and like creating your own graph paper over and over and over again is like by hand kind of stinks. So like I'm just trying to make it a little bit easier by there's a blank copy that you can just kind of cut and paste in there. But whatever works for you is fine.
So the first assignment is just the problems, right? And we're skipping worksheet 2.
We're not going to do worksheet 2.
Okay.
Yeah, we're not going to do worksheet 2.
So just
Worksheet 2 and worksheet 1 were like the same thing. So like I don't see any reason of doing it another one. When I looked at it, like worksheet 1 was just like graphing quadratic things and like describing transformations. If I look at worksheet 2, it's like the same thing. Describe the transformation, graph the quadratic thing. We're doing it once more generally, but like we've done examples with it generally, it's not any different. And then they have this thing, but this is still the same. It's like, here's your points to use, and like graph this. It's still the same thing. I don't know. I don't see any reason to worry about it. I'm more interested in coming and getting into the trig piece, I think. If you guys said that worksheet 1 wasn't a big deal, I don't see any reason in going back and doing more practice on it. Worksheet 2, that seems like just frustrating for everybody involved. You know what I mean? If you're like, ew, worksheet 1 was hard, then for sure you can do some more practice on worksheet 2. No biggie. But I don't think I'm going to assign it. Is that cool? It was like, yeah, one less thing for me to do. I'm cool with that. Let's go. All right.